Okay, thanks very much, Sergey, and thank you all for coming on a Friday afternoon when you could have been stuck in traffic headed out to your touches. This is an unusual thing with these free lecture things, of which I've given a few, that the audience to the third lecture is the real elite who are seriously interested in subject rather than just come to see the speaker. So I'll pitch my talk accordingly. This is going to be on open questions, and specifically open questions on which I've done some research, which has led to some results, but it's actually also gotten to a point where I can't really any longer claim to have any kind of property right in it. So anybody who gets excited and is able to make progress or suggest joint work to make progress, so I'm open to all kinds of things. I did mention both of these topics when I was giving the first lecture, and the first one I want to pick up is that of graduated punishments, and the idea is the following, to remind you. There's a lot of theory of repeated prisoner's dilemmas, and there's a lot of empirical case study and other kinds of evidence about them. The theory and the case studies are broadly agreed on most issues. So they all agree on the importance of patience, having discount factors close enough to 1 or discount rates that are small enough. They all agree about the importance of having a stable group of transactors and also usually a small group of transactors. They all agree on the importance of the precision of the monitoring technology, so cheating observable reasonably accurately, reasonably quickly, etc., etc. And they all agree on some other things that are maybe not quite central to the issue. But there's one very central issue on which the theory and the case studies diverge really dramatically. And that's about the kinds of punishments that will sustain good behavior. In the theory, broadly speaking, there's a presumption that the more severe the punishment, the more harsh the punishment, the better the cooperation that's sustainable in equilibrium. So the extreme of this, although this is not usually a part of the theory per se, but in many applied models, the way this is done is to have grim trigger strategies. So anytime any cheating is detected, the whole collusive agreement falls apart, and from there on the game will settle to the Nash equilibrium of the one-shot game. And if you ask people, why are we doing this? They say, well, this is the most serious subgame perfect punishment that can be levied, at least in simple context, and the most serious punishment is going to give you the most cooperative outcome. Of course, the theory has progressed way beyond that, and my colleague Dilip Abreu and a number of his co-authors have much more sophisticated papers on characterizing in a kind of fixed point way the most serious subgame perfect punishment that can be levied to sustain the best cooperation. There's also another branch of theory that argues that punishment should not be that serious, and this is basically to do with imprecise monitoring. So the Green-Porter model and things of that kind, where what's happening is that sometimes by mistake you will get bad outcomes when actually nobody cheated, and the serious punishment will get invoked, and that is actually costly to everybody. You want to reduce the cost, and so you want to reduce the level of punishment to some extent, at least. But there's kind of presumption toward harshness anyway. There's also literature that has punishments that are not constant through time. It's not the case that one-shot Nash is going to play it forever and ever more. And usually those kind of punishments, as in Abdur's work, will have an early phase that's particularly harsh, and then it will ease up afterward. The idea is that the easing up afterward will act as an incentive, act as a reward for people to participate in the earlier harsh phase, and so keep the whole structure subgame perfect. It's the interest of subgame perfectness that dictates the early harsh phase and the subsequent more relaxed period. A whole body of empirical literature finds that successful cooperative regimes work almost exactly in opposite ways. Punishments are usually very mild to start with. In fact, it may not be a punishment at all. If somebody cheated, you tell them, hey look, that wasn't the right thing to do. And they might make a little restitution or promise not to do it again, etc., and maybe that will work. If that doesn't work, you ratchet it up one level. And in a number of these stories, it might be kind of a mild fine that social pressures or some social adjudication mechanism will make them pay, or you might be entitled to to damage their property a little bit to inflict punishment on them, or things of that kind. And if even that doesn't work, then you can take more and more successive measures, of which completely breaking off the relationship is usually the very last one. Exactly the opposite of grim trigger strategies, where completely breaking off the relationship, basically, that's having no intertemporal cooperation at all, was the very first immediate step. And in reality, that's usually the very last one. Examples, you'll find a number of them in Ostrom's work of fisheries and other kinds of common property resource analysis. And also another interesting example is the number of American states that have these 3 strikes laws, that for a given offense, the first time you commit it, it will be a reasonably mild punishment, the second time more serious, and the third time you might be sent to prison for a long time. So a very similar sort of structure. So, can the mildness be explained by the Green Porter or its subsequent work kind of thing alone? Actually, there are 2 types of problems with that. One of them is, along them, there is no learning going on. There is a bad experience, and that bad experience is not really telling you anything. You're not kind of saying, hey, there's a bad experience, therefore, at the next phase I need to go harsher. There's nothing really changed. And part of the reason nothing has really changed is that in the equilibrium of those games, nobody is actually cheating. Nobody is actually cheating. Everybody knows that any bad outcomes that arise are purely a matter of luck. However, you have to go on going through the motions of those punishments purely to maintain their credibility. And that's not very realistic. We do observe actual cheating going on. And we would think that if really that was the story, societies would try and improve the technology, etc., in a way that would reduce that unnecessary cost. So both for kind of realism reasons and also the fact that you like to think that what's going on as a result of observing a bad outcome is some kind of Bayesian learning that we need, not merely imprecise monitoring technology. And that's basically a repeated moral hazard problem. We also need some private information. We also need repeated adverse selection. Combination of repeated moral hazard and repeated adverse selection makes this problem really difficult. And I don't know if you saw in the earlier slide who's working on this. This is a working paper that I've written with two co-authors, Dilip Abra and Doug Bernheim, and they are the real game theorists. I mean, if they can't solve it, maybe it's unsolvable. We have some examples, something to learn from those, but take that as a challenge if you like. Surely you have more powerful game theorists now who might be able to make the next crack at it, try and convert the example into more general theory, or see whether the kind of intuitions, the kind of ideas that come from the examples are actually borne out in the more general theory or not. So I'm going to present those examples for you, and the example particularly that I'm going to present is the opportunism problem of Williamson, or exactly what Griliches calls the one-sided prisoner's dilemma. So what's happening is each period, each stage game, these two people, A and B, and A can invest some money in B's enterprise, and B can either use it productively and pay A back, or run away with the money, or at least put the money somewhere aside, or not pay A back. So that's the one-sided prisoner's dilemma. It's B who's got the opportunity to cheat A. So specify stage game. If A decides to invest in B's enterprise, if he doesn't decide to invest in B's enterprise, so the game subsequently doesn't happen at all in that period, both of them have some outside payoffs, and there's 0 for B and lowercase a for A. Those are only normalizations. Nothing is really going to hinge on that being a 0 and that A being positive. We made that A positive rather than 0 because we don't like to carry negative numbers around too much. Later on in the algebra, you have to remember that certain number is negative, and it's easy to make little slips at that point. So nothing hinges on this. And then if A invests, B has a choice between two actions that we call variously either generous or honest, and on the other hand, selfish or opportunistic. And B will get a higher payoff by being selfish or opportunistic than by being generous or honest. And the difference in B's expected payoffs in the stage game from being selfish, we denote by Y. Right now this is a notation. Y is not a given number, this is just a letter. And we call that the temptation that B has to cheat. In various ways that's going to be B's type, that may be private information, etc., etc. So temptation is the name for that. Then as a result of this game, A will get some payoff. And that can be either good, that's say bigger than the A that this player A could have got outside, or 0, less than what he could have got there. A good payoff or a bad payoff. And that payoff is all that A observes. A doesn't observe B's type, A doesn't observe whether B acted selfishly or opportunistically. What differs is the probabilities. If B has taken the selfish action, then the probability of A getting the low payoff is mu, whereas if B has taken the generous, honest action, the probability of A getting the low payoff still is lambda. And we suppose that lambda is positive. That's it. Even if B has behaved honestly, it's possible that you get the bad payoff. You can't infer from observing the bad payoff that B cheated. That exactly is the imprecise monitoring technology in this case. And lambda is less than mu, so there is some way of differentiating between, probabilistically differentiating between generous action and selfish action. It's okay for us if mu is equal to 1. It's okay for us if every time B has behaved selfishly, A gets the bad payoff. What's important for us is that A might get the bad payoff even when B has behaved honestly. Now, we would normally just set this up in a normal way as a repeated game with a discount factor beta or delta or whatever you like, and that proved just beyond our capabilities. And so we took a cheating way out, which is this. At the beginning, while making this investment, A can commit to a punishment rule, which says if he gets zero payoff, an action will be triggered. At that point, A has no control over actually carrying it out. Outside his choice at that point, which will reduce B's payoff by Y. And that Y here is A's choice variable. So A can choose the level of punishment. And that will also reduce his own payoff by gamma times Y. It's costly to you to carry out the punishment. And this is our way of making it a genuine economic choice, how much you try to deter the other person's cheating. Now, again, we could in principle try to endogenize this in a repeated gain structure, but that was proving too hard, and our thinking was, we basically know how to do that. It's not something new that we are going to learn from this model. So let's not try and do it here. Let's focus on what are the really new issues of B being of different types. And we carried that to even farther extremes that we'll see in just a second. But before I come to that, let me explain what these types are. And they're going to be parameterized by theta. So that is going to be related to the temptation B will have. And A has a prior distribution over those thetas, and that distribution will be updated in the light of observation of whether A gets the good payoff or the bad payoff from one period to the next. And we'll look at two cases in which quite different things happen. One is the case where the temptation is non-stochastic, and theta is simply B's temptation level. So in that case, we'll use Y and theta interchangeably, basically. So theta person has temptation theta. And that's all there is to it. And there'll be a prior distribution over those thetas, which will denote by F theta. The other is the case of stochastic temptation. And that will mean that for any theta, Y is a random variable of which the CDF depends on theta. And that is distributed over a fixed support independent of theta. Otherwise, some kind of observation will clue you into exactly, at least within a certain range, what theta is. And so the idea here is between 0 and Y bar, there is this f of y theta that goes from 0 to 1. And if there is a bigger theta, it will shift to the right in the first order stochastic dominance sense. So people with higher theta in the distribution sense have higher temptations. Okay. There will be a prior over theta that, at least for the purpose of the handout, I don't need to write down. But those who want to really get the details of math in this, the paper is on my website, and you can also, if you wish, pull it down from that website and post it on this. Now, here's a completely drastic simplification. I'm going to suppose that at any stage game, both of these players are concerned only with payoffs in that stage game. Think of them, if you like, as kind of Lexan type beta delta people who even the immediate next period's future they'll discount completely, Of course, when the next period comes along, period 2 comes along, they'll care about period 2 at that time, but at that time they won't care about 3. That will lead to some kinds of problems. So there are some things in the paper where we actually do things more generally, but I want to keep things as simple as possible, basically so that I can focus completely on one thing, which is the tricks that Bayesian updating in this case is going to play on us. So I want to basically have nothing else at all, however kind of very odd in the context of what's really a repeated game looks like to you. So please bear with me. And again, if this is something that one of you succeeds in doing better, that would be wonderful. Let me then begin with the fixed temptation case. So here A had chosen a Y, the level of punishment that he is willing to inflict. And what that means is that all those types theta who are below Y are going to be deterred. By cheating, they'll get theta, their temptation, but punishment will lose them Y, and that's not optimal for them. So the punishment Y will deter all those people whose temptation level is below the punishment level, will not deter any of them to the right. So the probability that B will choose the generous or honest action is just the cumulative f of Y, where Y has been chosen by A. So what's the probability now that A gets the low payoff as a result? And that will be that B is acting honestly, but A gets low payoff anyway, that lambda, plus the probability that B is acting dishonestly times the higher mu probability conditional that A will get the bad payoff. And I denote that function by L of Y. And then A's payoff is going to be, if A gets the good outcome, which happens with probability 1 minus L of Y, that good outcome is a payoff of C. However, if he gets a bad outcome, which was 0 to start with, on top of which he is now paid gamma Y to inflict the punishment, multiplied by the probability L of Y. And that simplifies to that. So A will choose Y to maximize this. Then there will be an outcome. And the next period, A will see that outcome, revise that prior F to a new posterior, and second period game will be played, then a third period game will be played, etc., etc. So that is the structure of the non-stochastic temptation model. And let's ask, is this going to produce graduated punishments? Is it going to be the case that if you observe a bad outcome, the Y you set next period after you have revised your prior will be higher than what you had before? And the most surprising answer to us was that this is not correct. And the correct result is actually pretty dramatic. What happens is that if you get a good outcome, you make no revision of Y whatsoever. The Y that was originally optimal stays optimal. Whereas if you get a bad outcome, your new Y could in principle go in either direction. It could go up or it could go down. So in two ways, this is a little bit surprising. And again, I want to conceal the math and give you the intuition for why that happens. Can people see it now? I'm finding it a little difficult to see it from here from the light, but I can't help it. Okay, so let's suppose that in the first period, a certain level Y star was optimal. And you got good outcome. This is the case in which I want to argue that no revision will be made at all. what will then happen to the posterior distribution of types? What will your change in the estimate that the various probabilities of the temptation being less than y star versus being bigger than y star are? What will happen is that the likelihood of all temptations less than y star will shift up by the same proportion, whereas the likelihood of all temptations greater than y star will shift down by another different proportion. If you want to see a little bit, the base formula is really a mess to write out, but the simple way to see that is, let's suppose we've got a yi less than y star. So this guy is behaving honestly. What's the chance that you get a good outcome from him? 1 minus lambda times yi. And this will be divided by all that big sum that normalizes it. Whereas if yi is bigger than y star, the chance that you're getting a bad outcome from this guy is 1 minus mu times yi divided by the same old sum. Lambda is less than mu, you remember. So 1 minus lambda is bigger than 1 minus mu. So all of these probabilities are being blown up by a constant factor that depends on 1 minus lambda and this normalization, which again is independent of that particular I. Whereas all these guys are being blown down by a number which is again independent of the particular I that we've got here. That's crucial. And I call the factor by which all those less than y star are blown up k, and all those by which those greater than y star are blown down, the factor h less than y. So now next period has arrived and you are contemplating, is y star still okay or should I change it? Look at one experiment. Well, what would happen if I tried a slightly smaller punishment? I, as player A, will have 3 kinds of different effects on my payoffs. First of all, the true temptation might actually be even less than the y prime, the new smaller y prime. And if that's the case, I benefit. Call that change E1. But why? Because I'm now not inflicting a big punishment on the types in this range. I was inflicting y star before, now I'm inflicting only y prime unnecessarily. They're behaving honestly with either, and the smaller punishment is enough to do the job. It's not costing me that gamma times the extra y. What about those who are bigger than y star? They're not going to be deterred by y star, they're not going to be deterred by y prime. From time to time, I'll get bad outcomes, I'll inflict the punishment, I'll bear the cost, but it's not achieving any deterrence. So that cost is now less for me because I'm using only y prime, not y star. This is almost like this business of second price options, right, in the argument style. The key difference is for those whose temptations happen to lie between y prime and y star. Those two, the n ones were gains, this one is a cost, because what's now happened is I would have deterred these guys before. Now I can deter them, but I have to suffer the low payoff and incur the cost anyway. So there are 2 positive things and 1 negative thing. Previously, y star was optimal. So using the old probabilities, E1 plus E2 plus E3 was less than 0. That's just the definition of y star being optimal. What's happened when these probabilities have changed? E1 and E2 have gotten multiplied by k, the bigger than 1 factor. And E3 has gotten multiplied by that h, the smaller than 1 factor. collect the terms slightly differently. So take k times e1 plus e2 plus e3, and then adjust to have negative k minus h times e3, and see what happens. E1 plus e2 plus e3 is negative. K is positive. E3 is positive. K minus h is positive. So that whole thing is negative. So I can gain by going down to y prime now. I couldn't gain before. It's entirely possible that that was 0. This will be strictly negative. So maybe the optimum at y star previously was smooth. So for a very, very small change, there'll be only a second order loss. Now there'll be a first order loss. Carry out exactly the same kind of thing for attempting y bigger than y star. Sum of what's gain and what's loss and all that kind of thing will change, but exactly the same kind of thing will ultimately come through. It was not worth doing before, it's not worth doing now. And if previously the optimum at y star was a smooth one, now it will be a kinked one. Reverse the argument. What happens if you get a bad payoff? Again, that kind of a kink thing goes through, but now the kink is reversed. So if previously it was a smooth maximum, now it will be a kinked local minimum. And therefore, you will locally gain from departing from y star, either to the left or to the right. Whether globally the maximum will be to the left or the right, you can say. Of course, that doesn't prove that things might actually go the wrong way. You need an actual constructed example for that. But yes, I'll give you an example right now where actually that is just what happens. So this, of course, is with specific parameters. And here the cost of inflicting the punishment is 12. Gamma is 1, no big deal. Mu is 1 and lambda is 0.5. And three types of temptations, 1, 6 and 12. And the prior probabilities are a quarter, a half and a quarter. So you can then calculate what are the probabilities that A will get a good payoff or a low payoff, depending on the choice of Y. Only three choices need to be considered. One, which will deter only the lowest type. Again, I mean, there's a kind of exact equality issue, but think of that 1, if you like, as 1.001. So I can very easily break the ambiguity in favor of punishment of 1, actually deterring person 1. So if A sets a punishment level of 1, that means that the lowest type is deterred, but the two upper types are not. So what's the probability that you get a good outcome? The prior probability of B being of type 1 was a quarter, and in that case you got a good outcome with probability half. Therefore, the probability of a good outcome unconditional is 1/8. With 6, types 1 and 6 are deterred. And then the probability of getting a good outcome is the sum of these two, which is 3/4, half of that, and therefore 0.375. And you can work out all those kind of things like this, and ultimately work out A's payoffs, and it turns out that those are the numbers. With the result that deterring the two lowest types by setting punishment level equal to 6 is optimal. Okay? Suppose you do this, and suppose you actually get the bad outcome. What are the probabilities that that bad outcome could have come from various types? It could have come from the lowest type with probability half. So that's the total probability that that's the way it could have come about. It could have come about from the middle type also with probability half. And so 0.25 is the probability that your low payoff could have come about because B was of the middle type. And lastly, if B was a top type, he is not being deterred, and in that case, the conditional probability that you get bad payoff is 1. You would get a bad payoff with probability 0.25. And so in your Bayesian updating, the sum that I had over there is just the sum of these three, and that's 0.625. You divide each of these numbers by that sum to normalize, and you get the first period posterior, which will then act as the second period prior. So, do that, and these probabilities are 0.2, 0.4, and 0.4. Notice how the 0.2 and 0.4 are both 0.8 times the original priors, and the 0.4 is bigger. So the common factor that I mentioned, you see immediately here. You of course don't see anything about the factor being common on the other side because there's only one type there. But if there are more types, you'll see that as well. Okay, so those are the new types. You go through exactly the same kind of calculation, and these are as payoffs from the three choices. The middle one, which was the optimum before, has now become the pessimum. And the optimum is now at 1, not at 12. You got a bad experience, you lowered the level of punishment. Now, think about it. It's not so surprising after all. That's usually the case, right? So something sounds counterintuitive first, you think about it a little bit, you get a new intuition, and then you say, oh, it's perfectly intuitive. What's happening is that the probability of the guy being really, really bad has now gone way up. So if you wanted to up your punishment and deter this guy, it would cost you too much. Why not stick here? Well, you're not deterring this guy anyway. There isn't a great deal of probability that there's this middle guy. You might as well go way down. Now, whether as a result you take the low payoff or not depends on what your outside opportunity is. So if player A's outside opportunity was bigger than 0.3, he would just terminate the relationship and go outside. Otherwise, he would stick to carrying on this game, recognizing that this is a bad guy, that the chances of it being a real bad guy are quite high, at least for period 2. If there's again a bad outcome, there'll be more revisions, etc., and presumably eventually enough bad outcomes will suggest to you that you better quit this whole thing. But that will be as a last resort, not a first resort. So let me then go to the stochastic temptation case. Again, you can do a similar kind of thing and have A's payoffs given by much the same formula, except that now this probability of getting a bad outcome will be a combination of what happens over these types in various ways. And I did not write the formula, but since bold is nicely available, let me write it because it does actually suggest why the funny things that happen are going to happen. So L of y is now going to come from various types of B. And they might be indexed by I, and your probabilities of those might be pi I, and then you'll see what are the L functions that you get from those various types. If you set punishment y, then the probability of your guy behaving honestly is just the cumulative up to y of that type. And in that case, you'll get the bad outcome with probability lambda. With 1 minus f of y theta I, you will get a guy behaving dishonestly and getting the bad outcome with probability mu. So suppose there are just two types. You can very simply see what's happening. If y is 0, you're not deterring anybody. Your punishment probability was mu. So you're getting bad outcome probability was mu. If y is y bar, the full max, everybody is deterred, but still because of the imprecise monitoring technology, you're still getting bad outcomes with probability lambda. And as y increases, this will go down, and maybe if the distribution has quite a sharp peak, it will go down suddenly at one point. And that's exactly the experiment that I'm actually going to carry out, and you will see the result of that. That's one type. Another type might be something like this. And then, when both of those types are present with different probabilities, say half and half, what you will get is around here you will go only half the way, then you will stay flat for a while, and then go down again. Now look to see what that function c plus gamma y multiplied by this is going to look like. C plus gamma y multiplied by L of y, which starts at mu. So it will start by going like this with some slope. Then it will collapse suddenly. What's multiplying this? Then it will be c plus gamma y times a pretty constant thing that's about half lambda plus mu. Then it will collapse even more. And then start to go up with slope gamma times lambda. It's almost pretty inherently not a nice function. Now, that's being subtracted off and we are maximizing. So the nice kind of function would have been a convex one, but this is not convex. It could be convex under special circumstances. So if the basic distributions are normal with a sufficiently wide dispersion, then it will be convex to all intents purposes over what we the range we want. But if they're normal with small sigmas, then the function that you're trying to maximize will not be convex. And that's exactly what happens.
Avinash, may I ask you
sure.
a simple clarifying question for on the previous slide, on the fixed temptation. Is this true if you have two types, then if you get bad outcome, you always raise the punishment? Is this true or not? You have a nice example with three, but you have two types. Then it seems like from what you're saying, that should be the case.
Unless the cost of punishing the higher type is so high and the probability has gone so high that you just give up on punishing. So I think it's still possible.
Not strictly increasing, but
it could never go down, but it may not go up.
Couldn't go down. Okay.
Yeah.
Right.
Actually, good question. I mean, we never thought of doing it just for two, which is obviously what any sensible person would have done first. Don't know why not. So, there can be multiple local optima, and there can be kind of sudden changes of optimum as something underlying this changes. And we've got one example of that where there are just two types, a good type and a bad type. And the good type will have normally distributed temptation of mean 6 with standard deviation 0.14. 0.14 is kind of a square root type thing, so it's easy to program the error functions. But the important thing is that it be small in relation to the difference between these two means. And the bad type has a mean of 6, and again the same standard deviation. So that actually picture looks exactly like this. And all these various other parameters. And then we let the probability of the bad type, the probability of the 6 type, increase from 5% to 20%. And what happens is that for low probabilities, it's the lower of the peaks that is the global optimum. And then suddenly, somewhere in here, it switches from the lower one being globally optimum to the higher one being globally optimum. A little bit of surprising comparative statics is that while this pi is going up and the lower y star is the global optimum, it's decreasing. So the probability of the bad type is going up a little bit, level of punishment is going down somewhat. It's somewhat related to what we had before, but not the same thing. But if you do actually move to the upper one, then that one is going up. It's kind of bifurcation. You ease on the punishment while you're using low punishment, then suddenly jump and start to tighten it further. Now this is specific to this numerically calculated example. We have no idea of whether this is general or not, whether it's specific only to normals and wouldn't happen in some others. This is just kind of completely open. And I showed a kind of one extra in each case. These are local but not global optima. And you see how this number, the payoff from using the low-end punishment, or the locally optimal, is less than what you would get here from the global optimum, and conversely the local optimum here is smaller than the global optimum here. Somewhere in between, for like 0.133, the two would be exactly equal. And that's what this picture shows. This picture is drawn for the case where these two peaks are exactly equally high. And I mentioned the comparative statics already generally, except for some of these things. Turns out that both of these optima, the left-hand one and the right-hand one, are more than 2 standard deviations above the corresponding mean. So the punishment here is, remember 4 was the mean and 0.14 was the standard deviation. This is almost 3 times standard deviation, going down to maybe like 2.5. And likewise here, it's 2 standard deviations above, gradually going to more and more. So basically, at least in this example, again, we have no idea how general this is. If you're deterring a type, you're deterring it more or less completely with like 90% probability. And lastly, look at the V. It's decreasing, decreasing, decreasing. Then of course at the equal one it will be equal, and then decreasing again. But you already see here it's kind of flattening out. And that is one result that's actually perfectly general. This we can prove in a more general setting with finite discount rates, etc., that the value function is decreasing and convex. And that means that if you confront the decreasing convex value function with the outside opportunity A, it's going to fall below the outside opportunity only way to the right. So let's suppose your probability of the bad type through Bayesian updating is successively increasing. What will happen in this example is that you will be just slightly lowering your punishment level. Finally, you'll suddenly jack it up and keep on jacking it up, keep on jacking it up. And let's suppose the outside opportunities discounted present value was like 1.83. Once your estimate of the type being the bad type got above 15%, you would say that's enough, I'm quitting this relationship and going up. So that's the way in which termination of the relationship is a last resort and not a first resort. So there is a fair bit more in the paper that those interested can look up, but let me...
Excuse me, and
yeah.
how the level of punishment differs from from one period to first, second, and so on periods? Is it decreasing, increasing? So for this example.
So let's suppose you have bad luck, and you keep on observing bad outcomes.
Mm-hmm.
You had started out thinking that the guy was only 5% likely to be the bad type. You will increase your posterior probability of that, as in fact exactly in Katya's two-type example. Here there are two types, but with stochastic temptation. So successive bad experiences will successively increase the posterior probability of the bad type. So let's for the next period you think it's 10%. Then in period 2 you will decrease your punishment just so slightly. Yeah. Then again you get bad luck or a bad outcome. You will increase it still further. Then a time will come when you will increase it suddenly by a big amount. And after that we'll keep on increasing it by little amounts, etc. Till maybe a time will come when you give up. Of course it's entirely possible. Let's suppose your outside opportunity was 2. Then you would have given up before ever going to the right hand branch. So that possibility does exist. But in general, so to speak, you will go through these phases where you first of all decrease your punishment slightly, then jump up to a much bigger punishment, then slightly increase. By the way, that description again, let me emphasize, at least as far as we know, is specific to the normal. It may not hold up for others. But the termination coming last will always be the case.
One more question. What function F you use here for this picture?
For which?
For this picture.
So that F is the cumulative normal.
I see.
Yeah, mean 4 standard deviation 0.15, that's F of y theta 1, and mean 6.14 is the F of y theta 2.
What would happen if the standard deviation increases?
Yeah, what will then happen is that a time will come beyond which this decrease will be kind of pretty smooth. This other decrease will also be pretty smooth, and the halfway between will be smooth enough that this function will be everywhere where you're most interested in it. It may not stay quite convex right at the end, but where you're interested in it, it will be convex. And then you will have a unique, regular maximum.
Convexification of the problem.
Yeah, exactly, defined by the first order condition.
Does it depend?
It's the usual kind of thing that smearing it with a large standard deviation is conducive to.
Does it depend on the assumption on the normal distribution?
With normals and sufficiently large sigmas.
No, it's okay, but
no, it doesn't have to depend on normal. For a lot of other distributions, again, you can get convexity, and in fact, if these cumulatives are kind of nicely convex in the first place, you'll be pretty good. So if the density of the bad types is monotonically increasing, then you'll quite likely be okay, and things like that.
And do you have some results if delta doesn't equal 0?
The decreasing and convex field, yes. That's about as general as you can ask for, and that's done by very standard dynamic programming, Lucas-Stokey-Prescott type argument. It takes a long time to actually carry it through successfully, but that's a very standard dynamic programming argument.
Delta, you mean discount rate?
Yeah.
Okay. No delta.
So, we hope we have kind of made some progress, found some interesting results that you might not have thought of when you first saw the problem. So, we allow types, which is not all that common in this kind of context anyway. The idea that basically your observations are giving you information about types and you're using that for updating, which is the key thing here. Get some useful things. Some results come out clearly, like breaking should be the last resort, and the new possibility that after you've thought about it makes perfectly good intuitive sense also is useful. But hey, I mean, this is examples. If we send this paper to Econometrica, they would laugh at it, right? So we haven't. In fact, we are still sitting on it and hoping to do some more work, but it's we're finding it extremely difficult to get three of us together and put in any work. So anybody who wants to take this and make any progress with it, it's public property. Let me then a little bit quicker tell you about another possibly interesting project, which is even more incomplete. There are kind of a few weird assumptions that I have to make for tractability, but the problem in principle is interesting. And that goes back to the story I told of the origins of the Sicilian mafia, where the idea was that the absentee landlords started hiring the toughest of the bandits as their guards. The first thing that kind of starts to suggest this to you is that there are people who are making a choice between being bandits and guards. Ought to be something like an occupational choice model. What are the kinds of models of this kind that exist? A number of people like Schleifer, Skakardas, and people have worked on this. And the usual kind of story is that one person divides his or her time between farming, protection, and banditry. So you farm between 9 and 5, then between 5 and midnight you guard your own farm, and then between midnight and 9 a.m. you go and rob other people's farms. It doesn't really make sense. You normally think of an occupational choice as a discrete thing. You choose one occupation and that's what you do, and there are kind of good reasons for that. There are kind of underlying economies of scale or a lumpiness that in training that makes you stick to one occupation.
On the national level, though, it works exactly like that. So each nation is engaged in all three of those activities.
Oh, sure. But then you want to take a population and say this faction will do this, that faction will do that. And also you want to allow some heterogeneity of the population. You want to allow some kind of a comparative advantage in being a bandit versus being a farmer. You'd think that there's a kind of two-dimensional skill space, right? Your skill as a farmer, your productivity, and even three-dimensional, your skill as a guard versus your skill as a bandit. And people are distributed, smeared continuum population over this three-dimensional space, possibly correlations, possibly not. So I just want to mention this because that tells you how hard that general problem would be to make assumptions about three-dimensional density function and including the possibility of correlation. So I went completely drastically the other way by supposing that just one-dimensional heterogeneity indexed by this parameter t between 0 and 1. And I assume uniform distribution for calculation purposes. That's not all that important, but some closed form solutions required. I interpret that T as toughness. And I just assume that the correlation is perfectly negative between toughness and farm productivity. So a T guy has T toughness and 1 minus T farm productivity. There are these wimps who are very good at farming, and then there are these tough guys who are very good at robbing the wimps. What are the occupations you want to think about? You can be a full-time farmer. And if, as a T person, you're a full-time farmer, your output will be 1 minus T. And you can hire a guard and pay that guard a wage W. Now, here's a kind of bad assumption that I've got. Basically, I confess completely it's bad, but I just couldn't solve it otherwise. And again, that's why I'm kind of offering this up for anybody who wants to make progress with it. The assumption is that you cannot observe a person's toughness. So you can't pay W as a function of T of the guard you hire. And this is going to be key. So almost in a sense, if the farmers hired the toughest bandits, how did they know that they were tough? This is not going to work, and that's the one respect in which, most importantly, I want to improve on this model. Instead of hiring a guard, you could become self-protecting farmer. And that's where you would put a fraction y of your income to guard your own farm, or fraction y of your time to guard your own farm, 1 minus y to farm, and in that case your output would be 1 minus t times 1 minus y. With a probability that you'll actually get to keep it, because you might still get robbed. You could become a professional protector, and if you did that, you'd get the wage W. And type T, I'm assuming, is not signalable or anything. And then you could become a bandit. And again, a bad assumption. I'm supposing that you start your work at 10 o'clock at night or whatever, you toss a coin and decide which farm to go to rob. You choose to visit a farm at random. That's the key. And what's more, you do this not knowing whether that farm is being guarded or not. Again, all of these are not good assumptions. They're being made solely because that's the math I could solve, and hoping that it will be possible to do better. So what happens if a bandit hits a farm that's guarded or not guarded? Not guarded, he just gets it. If it's guarded and the protector has toughness T prime and the bandit has toughness T, the probability that the output is retained, that the guard will beat the bandit away, is given by that formula. Again, linear because that's what I could solve. And of course, then you have to ensure that k is small enough that this will always stay less than 1 and all those kind of things. And I'm supposing that if multiple bandits hit, and this is going to be a kind of low probability event, but you have to specify what will happen in that case, they will surely get all the output and share it equally. That's not very good either. You could set up kind of a fight among the bandits. They come to the gate of the farm. First of all, they'll fight with each other as to who gets to go in, and then there's a fight or a variety of ways you could think of that. And all of these are... I want to think of this in a situation where there are actually lots and lots of farms and lots of bandits. And I can work out if there are F farmers and B bandits, both of them large number, then the probability that no bandit will hit your farm at all is given by that, approximately. This is one of these Stirling's formula type calculations.
And how the time you guard your own farm influence?
So what will happen is that you will be there at kind of random times, and you will calculate an expected value that the bandit comes at a time when you are there versus you are not there.
So if I guard my own farm when bandit come, this is the probability bandit is defeated. But if I don't guard,
if I'm not guarding it at the time, then it's gone. And the probability that exactly one bandit, a particular bandit, one of the B bandit hits is given by that. And this is kind of fun math to do, even at this level. Not often that economists get to use Stirling's formula and things of that kind. But actually, the economics of it needs to be improved in rather too many dimensions. There is a short paper that I've written that if people get interested, I'll send it along. I don't think it's part of a variety of things that I say. Then I set up a candidate equilibrium, and I verify it out that in general, this is what will happen. The ones with the least toughness will be full-time farmers. So they will get 1 minus T of total output. They'll hire a guard, and the probability of retention, etc., will then deflate that 1 minus T a little bit, but in general it will end up looking like this. The income you get from being full-time farmer. You can be a completely unprotected farmer, and this is the range that might most likely simply not exist. But there are cases where it does, because there's still the probability, the positive probability that no bandit visits your farm at all. So this will definitely go if the information as to whether a farm is protected or not is available publicly. But that's the kind of next line. So these guys are productive, so they want to farm, but they're willing to take the chance and save the W by neither protecting their own farm nor hiring a bandit. And in mathematical terms, the way this comes about is when you do the optimization with respect to that Y, you realize that there's a possibility of a corner solution, and you investigate when that corner solution actually appears. Then the third lot are the ones who are self-protecting. That's a convex function because as you get tougher and tougher, the kind of way in which the time you devote goes, etc., the probability that you retain output gradually increases. You don't lose so much of it. Finally, this is the income of those who choose to be the protectors. And this is the income of those who choose to be the bandits. And that's the general nature of equilibrium that will look like. Look at this, and to the extent that this is valid at all, there is something really remarkable. The protectors of the whole society have the lowest income. So, maybe that's true. Actually, in a lot of societies, the police are very badly paid relative to industrial workers, etc., etc. And it may make sense and may start to explain some other things also.
But that's because they're not getting their incentive wage. That's because in your model,
Yeah.
you're getting paid no matter whether you're successful as a protector or not.
And what's more, it can be conditioned on your toughness because nobody can observe your toughness.
Not only on that, but also on whether the robbery was successful. If
Yeah.
that happens. So who cares if you're allowed to...
Really richer problem will also allow moral hazard. For me, whether the robbery is successful or not is purely a function of the two types toughness and not how hard they try to.
But then that's a reverse selection thing, which is also assumed away here because you cannot condition your pay to the guard on his or her success.
It exists, and you have to calculate expected values. So the fact that the probability of success depends on toughness, etc., doesn't go away. It's simply that you cannot condition payments on it, etc., etc.
And you're not really conditioning your payments on whether the protection was successful?
Yeah, you're not, because nobody has different degrees of trying in this model. There's no moral hazard. But there is heterogeneity, and you have to take expectations over that heterogeneity.
Yes. I might want to pay more to more successful cars just to make sure that the tougher people come to serve me as protectors.
Okay. So you're thinking of actually a kind of screening mechanism. Yeah, okay. No, that's not here either. No, that's a very good point. I don't know if that's even doable, but that may be a way of...
I think I've lost you somewhere, and I just want to ask another clarifying question. It seems to me from the setup of the model there should be possibilities for multiple equilibria here. Sometimes, I mean, it just like in this analysis, you somehow keep the number of bandits and like all the shares in the population of different occupation constant. But obviously, like if many people are going are robbing, maybe having your own fun makes no sense anymore. Something like that.
Actually, there are. That's a good point, but there are equilibrium conditions. So what's got to be the case is that all of the total number of protectors hired by this lot have to equal all of the protectors that are here. And those kind of equilibrium conditions go to determine these T1, T2, etc., etc. Second thing is that the relative slopes of these things are determined. It's always the case that this curve is flatter than this one. And so things can intersect only in that direction. And since you're looking at the upper envelope, so there isn't going to be the kind of multiplicity that you are worried about. Sorry, I was kind of skipping too many details and never even mentioned that the equilibrium condition that the total number of guards demanded equals the total number of guards supplied is a part of this, but it is. Thanks. So, only the second toughest bandits are becoming guards. No, not the toughest. And, well, it may well be that nobody had real knowledge of who the toughest was and so on, but the greater likelihood is that in this case, there are enough kind of defects in the model that need to be fixed, and I will at some point return to this, I'm sure, but with luck, one of you will be able to do it much better and much quicker.
I think this is a fundamental feature of the model, which would prevail in whatever setup. The bandits keep the output they rob for themselves, while the guards for hire get a wage or get a share. So you need to sell the protector your property rights eventually. So the protector is a residual claim. So otherwise you would have the result anyway.
Yeah, good well.
Exactly.
If you manage to do the screen right, then it might be that the premium for successfully deterring the robber will be high enough to make sure that the toughest guys become guards rather than robbers. If the premium for being successful guards is high enough, which is what may come with screening, which you assimilate.
I don't see that because you never can beat 100%.
Marginal has to be greater
Margin
than
has to
100%.
be above 100% because the bandits get the full return to their toughness.
Oh, actually, only with probability.
Only with certain probability,
Yeah.
which makes a lot of
Okay.
sense.
Oh, okay.
Yeah.
Okay.
Oh, yeah.
Liquidity constraint.
No, that's true. It's conceivable that sort of the second toughest guys are the bandits, and they get the output with somewhat lower probabilities.
Okay. Because
that's
they
the
don't
latter thing. And the toughest guys are being paid enough of an incentive wage that's steeper. Yeah, that's actually a good idea what you're doing. Maybe you would like to think of a way of doing that and do it on your own. If you'd like to involve me, I'll be happy to do one way or the other. That's a good suggestion.
And field experiments.